So let's look at the problem. Well, let's talk about elevators in general. So there's a couple elevator problems here that you'll encounter. First of all, in an elevator, what pulls the elevator up? The cable. There's a cable attached to a pulley, spooled over a pulley. You get in the elevator, and then you get out of the elevator, and magically you're different elevation. Right? So it's the cable. So what force makes the elevator go up? Tension. If you're standing in the elevator, does the tension force cause you to accelerate upward? Directly. Does it directly cause you to accelerate? Not directly. It's responsible for you moving up, but it isn't the force directly responsible. Unless we're talking about gravity, electromagnetism, or other field forces that can act at distances, things need to make physical contact in order to exert forces. So what force is actually causing you to move upward in the elevator? The normal force, right? So let's say that we're going to stand on a scale in here. Stand on a bathroom scale. This is very, very famous physics situation, okay? Because what do we talk about the normal force? What do we talk about your sensation of your weight is really your sensation of what? Didn't we talk about that? Your sensation. No, that. Getting my classes mixed up. Video editor, can you edit this part out of the video? Thank you. Oh, sweet. I was talking to Nolan because it's not going to get edited out of the video. Okay, we didn't talk about this. Your sensation of your weight is not your weight. Like, you don't feel your weight. You don't. You might think you do, but you don't. If you were in intergalactic space, billions of light years away from any source of gravity, you would not feel your weight, right? You wouldn't feel it. So your sensation of your weight is not actually your weight. If you're in free fall, if Evan's in this elevator and Gia comes along and he cuts the cable, what's Evan gonna do? He's not standing on the floor anymore. He's coming up off the floor and he's chilling, right? The thing is if this was frictionless as the elevator was falling and it made no sound, Evan would just be floating in there. And he wouldn't even notice anything weird until he hit the ground, obviously. But the only reason that you would know something crazy is going on is because you would hear it, right? And you can feel the rumbling and stuff. But if you got rid of all that, you wouldn't even know it. You would just be like, wow, I'm weightless right now. Even though you would still be right here at the surface of the earth and you would still have weight. But you wouldn't sense it. You'd be weightless and you'd have that feeling in your stomach that happens when you feel weightless. So hopefully you'll never have Gia. Don't do that. So what is your sensation of your weight? Now, some people in here work. Some people in here, when they go to work, they have to stand the entire time. And when you have a job where you have to stand all day, what part of you is a little sore? As long as you don't have a bad back or bad knees or something, what is sore when you get home? Your feet, especially. Your legs, too, because they're attached to your feet.
I think
So, well, if you're doing stuff with your arms, then yeah. If you're not doing stuff with your arms, then why your arms? So yeah. So it's not your weight isn't your sensation of your weight. It's not that force. Your sensation of your weight is what force? The gravitational force is your weight force. But that's not what you feel as your weight force. Your feet get sore because what? Because the normal force. Right? Without this normal force in the way, we'd be in free fall and we'd be nice and relaxed. Right? To truly be in free fall, it's like being in a sensory deprivation tank. Right? You wouldn't feel anything. Right? Once your stomach got used to it and you didn't have that weird nauseous feeling. Right? Nauseous, whatever you want to call it. Yeah.
Isn't that like, you're talking about the elevator, and you know how when you're going up, that feeling you get?
Yeah. That's what I'm getting at. Yeah, because we're going to talk about that feeling in the elevator. I'm just trying to get there. Yeah. So bottom line, the sensation of your weight is the normal force acting on you. This is why when you go over a hill on a roller coaster, what happens? What do you feel like at the top? You feel lighter. Mm-hmm. The normal force is not as great on you then. Guess what? If you go fast enough to where you actually break contact with the ground, you jump, the normal force went to zero. That's the condition necessary. If the normal force is zero, you just jumped, right? If you go down a valley, like through a valley on a roller coaster, don't you feel real heavy at the bottom? That's because the normal force is bigger. for reasons that we'll learn when we do circular motion. So what I'm saying is, and so how this relates, like Stanstein says, when the elevator starts accelerating upward, what do you feel? You feel heavier. You feel like the floor's pushing on you upward, which it is. You also kind of feel like you're pushing downward, and that's because of Newton's third law. Yeah, the elevator pushes up on you. And if you're accelerating upward, what direction does the net force have to point? Upward. So, and actually, sorry, this is first, before acceleration. So let's say bottom floor. Bottom floor, at rest. This is me, not me, I didn't do it. Liberty did. This is Liberty in the elevator, bottom floor, at rest. What is Liberty's free body diagram?
One down, one up.
One down, one up. mg down,
Yeah.
normal force up, right? At the bottom floor, at rest, before the elevator starts accelerating, what can we say about both of these? Equal. Which means this is the normal force that you experience as normal, right? As typical. I shouldn't say normal. There's two different usages of normal. Yeah. This is the normal force that you feel as your typical weight, right? But then the elevator starts accelerating upward. Accelerates up. When the elevator is accelerating upward, what direction does the net force point? Up. Does your weight force change?
No.
No, your weight force did not change. So in order for the net force to end up pointing upward, what had to have happened? The normal force had to increase. How does it increase? Because the elevator is trying to move up because the cable's pulling it up, right? So it's going to put a normal force on you that is greater than your weight force. And since the normal force is the sensation that you have of your weight, you feel heavier. Now, what happens when we're moving up, but now we're at constant speed? What does the free body diagram look like?
We're equal.
It's just like this first one. I think I made this one too long. If I'm moving at constant speed, what's my acceleration? Zero. Net force zero. Newton's first law applies. Forces are the same. So free body diagram is this. Just like this one. Literally the same. That's why for most of the elevator ride, you feel like you do normally, right? Feel like you do normally because the normal force on you is what it is normally. And then we slow down to a stop. At the top, however high we went. So we're moving upward, but we're going to slow down and come to a stop, which means our acceleration has to point where?
Down.
Down. And if the acceleration points down, the net force has to point down. Newton's second law. Remember this, guys. Newton's second law, net force is mass times acceleration. That's a vector equation. So the magnitudes of each side has to be the same. But whatever direction the net force points, so does the acceleration. So net force points down. Again, is the weight force changing in any moment here? mg is not going to change unless you're like scarfing down a huge meal during the elevator ride. Your mass is not, your weight's not going to change. So as we slow to a stop, to get that net downward acceleration, what must happen to the normal force?
Decrease.
It has to decrease. It has to go down. So at the top of the elevator, your weight hasn't changed, but to get that downward acceleration, I need to have a smaller normal force. What is that sensation to you? That you feel lighter. That's when you time it right, you jump at the top, right? You jump at the top and you seem like you're in the air longer than you should be. Or you jump at the bottom right before you start accelerating up, that's harder to time. You do that and it feels like you're not on the earth, right? It feels like weird. And you know why that is? This is fundamental. So if you want to know some fundamental ideas of physics here, Roger, what are you doing? Okay. Well, listen for a minute. Are you really working on your quest? I believe. That don't show me your commitment. I love that. What are you doing over there? I'm doing what you told me to do. Oh, because what's on the computer screen now is exactly what it had to have been 2 seconds ago. I'm not accusing you of anything. I'm just saying that doesn't prove anything. Okay, what was I saying? What was I saying before I rudely interrupted myself?
Something about fundamental.
Jumping in elevators.
Oh, yeah. So, no, I don't know if you've noticed or not, but I mentioned coordinate systems once or twice this year. I mean, right? I'm underselling that a little bit. Yes, I talk about coordinate systems all the time. And I tell you all the time that all coordinate systems are valid, right? As long as we're careful with our measurements. That's not entirely true. Because guess what? In the elevator, when it was accelerating, things did not behave like they should. Right? I jump at the top when this is going on, and I'm in the air longer than I should be. And I look around. I look around in the elevator. What's going on? Oh, thank you so much. Oh, you guys are the best.
It took a little while to find you, but
Why did it take so long to find you?
because we went upstairs and
Oh, no. Oh, no. Well, I appreciate it, guys. You guys are the best. I appreciate it.
bye.
Have a good one.
Bye.
See you next time. No, these are good ones.
Can you loan us some, you know?
No, I don't know. What was I saying now?
Jumping in elevator. We still.
It doesn't behave.
Oh, yeah. So, and then this is, like, if you want to know physics at a high level, this is kind of where it starts. Because one of the main postulates of relativity, Einstein, is that all coordinate systems are equally valid. It's an idea that was known before him, but that's built into the theories of relativity. And the thing is that it's not entirely true, and that's not exactly what Einstein said. Really what he said was all inertial reference frames are valid. Measurements in all inertial reference frames. All that means is that non-accelerated reference frames. When you're in the elevator is your coordinate system. To your brain, that is your coordinate system. That is what you're referencing motions of things with respect to. The inside of the elevator. That's your coordinate system. If that elevator is accelerating, then things that happen in that coordinate system do not behave like you expect them to in a non-accelerating coordinate system. Hence, why, if you've never done it, try it. It's weird. Jump right when the elevator starts to slow down.
Oh, I've done that.
Or just after it starts to slow down, like jump as high as you can, and it will feel weird.
That's a normal thing. That's a normal thing to do.
Yeah.
Never heard of it.
When I was a kid, literally every time I got in an elevator, I tried to do that. Thousands of times I've tried to do it.
I'm trying to tell you not to.
Almost every time, probably. All right. But anyway, so what I'm saying, and we'll see this when we do circular motion stuff, when you have an accelerating reference frame, things appear visually to not be working normally. It seems like physics isn't working right. But again, that's only if your reference frame is accelerating. How can I do a problem with this kind of stuff? Let's say you know the person's weight is 100 newtons. But you know, and you're standing on a scale. This normal force, how do I measure normal force? I stand on a scale. Okay? So I measure my normal force. So let's say I have to calculate the normal force. No, let's say the scale reading is 90 newtons. Right? I know there that I'm accelerating in which direction?
No.
I'm accelerating down. Right? I know the net force is what?
10 Newton.
Technically it's,
Wait, say it.
in our standard coordinate system, it's negative 10 newtons. Right? Because mg would be larger, but it points down. Yeah. So what's the acceleration there? Well, you can calculate that using Newton's second law. Right? Just know that the scale reading. That's what you read, by the way. This will be the last thing, I promise. That's what you read when if you're like me, and you maybe have the opposite problem, I don't know. At the beginning of the year was the love handles I was trying to get rid of. I was having trouble with those. But I ended up getting rid of those when I got sick and could barely eat. So that was great. Now I'm having the other problem. Now I feel too skinny. Anyway.
Too skinny.
Yeah, dude. When I get sick, man, I can't work out for like
There's
weeks.
this thing called
Yeah,
a
just-
healthy weight, and if you go going
Yeah.
over it, it's really not helping.
And then my wife doesn't like it.
I never feel skinny.
My wife starts telling me, you're too skinny. And I'm like, oh, man.
Well,
She's
that's not
noticing.
helpful.
She's mean to me.
Right? Because you should like divorce rice.
What?
Right? Was you should divorce her on
No. She's pretty. Come on, projector.
It doesn't want to cooperate.
What am I doing right now? What am I doing in my life?
You guys about weight. Yeah.
There we go. This week has not been a great week. I promise I'll be better. I'll be better. No, as far as like me just, being terrible at teaching.
That's
You're
always.
not bad at teaching.
That's a normal thing.
Okay.
That's just a
What?
normal.
What was that?
Marissa, breathe.
Carolyn, what's going on over there?
Breathe.
I don't know what I should be concerned over.
Ain't nobody got time for this. Okay? Come on.
If you're laughing, that's all in the recording.
Yeah, this is all on video. Whatever you said is on video.
But you can
That's bad and will be used against me.
I'm gonna enhance the audio and find out.
Enhance the audio. What kind of movie Jason Bourne movie is this?
Yeah, you just push buttons and it magically makes it perfect, like in the movies.
Yeah, I enhanced the audio.
Okay. So, did I plug this in?
No. Yes.
Yeah. So it looks like I weigh about 724. Oh my gosh, what is going on?
It's going down.
This has been doing this all day. I have no idea what's going on.
215 units. Negative one.
A little over 700 newtons, right?
Yeah.
Is that reading my? Is that telling me my weight?
No.
What's it telling you? What?
Force between you and
Which is
normal force.
the normal force. No, you're right. So scales, the scales they use at home, they
English.
I can't English. They don't measure weight. They measure normal forces. How do I know that? Well, I can change the reading there. Do I look heavier now?
Yeah.
Can't
Right.
see it.
Did my weight actually change just now?
No.
No. I'm just pulling up on the table, which Newton's third law says the table is pulling down on me, pushing me down into the scale. The scale's not accelerating, so with that increased force downward, the resulting normal force must increase. That's what gets read up there. That's what gets read when you get on the scale at home. So if you're like me and you want to weigh a little more, then you just push it a little bit. If you're like other people, you want to weigh a little less, you just lean on the counter a little bit. So anyway. So again, scales read normal forces. Your sensation of your weight is a normal force. And then that's it. Am I really still on video?
Yeah.
Yeah, that's still on video.